This is Mark with your Advanced Assembly Technology Minute.
Electromagnetic fields exist throughout the universe. Charged particles rearrange the fields, and the fields in turn exert forces on the charged particles. This interactive dance is fast, but it's not instant. The rate at which changes happen is often called the speed of light, but really it's the speed of causality. The speed at which a conductor can cause a change in the electromagnetic field, and the speed at which changes in the field can cause a change in the conductor. When a potential difference is established along the length of a conductor, charges begin to migrate. As the charges move, they store energy by rearranging nearby electromagnetic fields. The change in the electromagnetic field will cause charges to move in nearby conductors. This is the source of near-end and far-end crosstalk. When the potential difference is reversed, or removed from the conductor, energy from nearby fields can move back into the conductor. Where things get interesting is when changes in the conductor happen so rapidly that the surrounding electromagnetic field doesn't have time to establish a steady state or return field energy to the conductor, and the extra energy radiates outwards into space. That energy will eventually find some conductor nearby that can absorb some of the energy. This is the source of electromagnetic interference. The electrical engineer's job is to manage the electromagnetic fields in their circuit. And here are a few tips for your next design. First, pour copper everywhere on your internal and external planes, and then stitch those copper pores to your ground plane. The artwork you submit to your fabrication house is not the artwork that is used in your PCB. Fab houses often have to add copper thieving pads to ensure proper plating thicknesses. Copper thieving pads can act as unintended absorbers and radiators of electromagnetic energy. As an added bonus, the copper pores will help prevent the warpage of your PCB during assembly. Remember, if you don't add copper to your board, your fabricator will. 2. Always provide a return path that is adjacent to your signal trace. A return path that is directly above or below a trace is usually better than a return path that runs alongside a trace. Remember that if you change layers, you need a vertical return path made of vias. If you break the return path, the signals will radiate to other places in your circuit or out into the environment. 3. Signals stop at copper pores. Whether that's a ground plane or a power plane, never try to couple paths through a conductive plane. It doesn't work. The signal will use the closest copper as its return path. 4. Don't build antennas into your board unless you truly mean to design antennas in your board. Test points, unused route paths, and slivers can wreak havoc on your design. Never put a test point on a truly high-speed differential pair. 5. Use vias to stitch the various planes of your board together. Create a single uninterrupted piece of copper wherever you can, and use vias where that isn't possible. I hope you learned something. We'll see you next time.
If you liked this video, let us know by clicking the like button at the bottom of the screen. But don't stop watching now. We have other educational and informative videos on this channel. To learn more about what Advanced Assembly offers and how we can help you, please visit aapcb.com.